Welcome to Seed Lab. We did an autonomous robot, and it's by Ryan Reschek, Doyle Smith, Mia Werlin, and Eric Salazar. Okay, introduction. So the main function of the robot was to have it navigate an obstacle course. It detects Aurco markers using a camera that are placed about 1 feet apart. The information communicated between the Raspberry Pi and the Arduino via serial communication. The Arduino controls the motors, how fast they spin and rotate around the obstacle course, and we repeat this until the destination is met, and the turning and continue repeating until the obstacle course is navigated.
So how we designed the bot was simple. We have 2 wheels for rotating the bot as well as moving forward. We have a Arduino on it and a motor controller on the Arduino and a Raspberry Pi that talks to an LCD screen and to the Arduino. And it does this because it has the camera that's connected straight up to the Pi. All right, using computer vision, the bot detects the Aurco markers and it finds an angle and position. Then it spits out to the Arduino where the angle and position is of the markers. Using feedback control, it uses proportional and integral control to keep a constant feedback loop of reducing the amount of error that there is in the system to the point where it gets to the destination at the right angle.
But we'll get into that, into each individual section in the next slides.
So contrary to our previous exercises where we would take photos and perform math on each individual photo and work with the Aurco markers in this sense, we now are using a video feed to identify and see these Aurco markers. So since the video feed is fairly heavy on the system, we initially converted it to grayscale so that it processes it much faster in order for speed to be of the utmost importance. So what we do is we take an individual frame from our video feed and we perform a Aurco detection similar to how we did on individual photos, as a frame is essentially a photo. So this allows us to get the real world values such as the distance and the angle relative to the camera's position to the Aurco marker. So for our final design, obviously we hop from island to island, from beacon to beacon, and we control the order of the Aurco markers, which allows for the camera to check against an ordered array to ensure that we are seeing the Aurco markers in the correct order so that we don't go in a wrong order around the beacons.
As Doyle said, he talked about the camera part, but as far as the rest of the system goes, here's a basic diagram of how it all functioned. The bot first looks for the camera, as Doyle just mentioned, and it receives an angle, or more like generates an angle and position, as well as IDs from the camera. The camera then will detect many other different IDs, but then it selects the right one based on the array it gets. Once it gets that, it then sends the correct angle and position associated with that ID to the Arduino drive. And it then, on the Arduino end, waits a second for it to calibrate. The Pi then waits for another camera angle and position because it needs to wait for it to get the right updated one. Mainly what happens is the bot stops and then it needs to wait for it to get the right angle and position. Once it sends that again, the Arduino does its thing. It turns to the right angle to the Aurco marker and drives forward. That will be talked about in the next slide. And then it repeats this step when the Arduino sends a command back saying, hey, we're ready to start searching again. That happens in the circle state.
So the primary function of the finite state machine is to determine the behavior of the bot at different times, and necessitating, because of the function of the machine requires different types of behavior depending on the task being performed. There were several different states that the robot entered into, the list of which is searching, calibrate, turning, forward, turn 90, circle, and wait. These states were cycled through. Searching was the initial state that was used to determine the location of the first marker. in which it turns slowly to search for it. Calibrate is the state that's used in order to assure that the angle received by the Arduino is an accurate one. Turning is the state in which it orients itself relative to the marker it is going towards, and then forward is when it approaches the marker. Turn 90 was included in order to make sure that the circle state would make an accurate circle around the marker, because otherwise it would do so at an angle. And then circle was obviously designed in order to allow the machine to circle the marker. Later in the design, it also incorporated, as Ryan earlier said, the addition of serial communication. And then wait is the final state in which it ceases to move. These states were looped through depending on the order of the marker that had been detected by the Pi and the information that is given to the Arduino. This allows for each of the states to handle their own function independently using dynamic monitoring of the wheel positions and the distance and angle of each of the wheels relative to the desired positions. Each of the motor functions were also controlled within the states individually, such as the enable pins controlling the directionality of the wheels, which allowed it to do things such as turn in different directions and go forward relative to the position of each of the wheels, as well as the voltage control, which controlled the forward speed and allowed for adjustment of the speed and motion of each of the wheels, and control of the rotational speed, again, through adjustment of the individual speed of each of the wheels.
As for the localization subsystem, localization means converting the code, I would say, or PWM into real position and velocity. So first, the motor encoders are read via the Arduino, and with that, we convert the encoder counts to angular position / velocity using the equations listed below. And from that, we use the radii and the distance between the wheels to find the velocity and the real position in real time via the equations below as well. With the Simulink model and the data, we use that to calculate the KP values in order to reduce steady state error and use that for the feedback loop.
Okay, so on the screen, you can see the raw data for both the phi and the rho values, which were what we measured as discussed in the previous slide. And then below them, you can see their respective MATLAB models that we used Simulink models to create appropriate transfer functions in order to have an appropriate model in order to perform our experiments on. Below, we have the experimental setup for the Simulink models. The first is the tuning of the two transfer functions for the phi and rho values. And then directly below that, we have the two tuning setups for the rho and phi values in order to create the k, p, and ki values required to run the feedback loop in the Arduino. And then directly below that, we have our super loop for the selection of the phi, aka the turning rate for the Arduino, in order to make sure that we have an appropriate angle that is reached after our selection.
Here's our fully working prototype. The bot initially searches for an Aurco marker, then it goes to it and rotates it, as Mia mentioned earlier. And then repeats this, hopping from one island of markers to the other until it reaches the final marker. Once it gets to the final marker, it makes sure that it's the final marker and by keeping a tally of it. And it does a half circle on purpose.
In conclusion, we have a working bot that uses computer vision to detect markers and calculate the relative angle and position of those markers. Through system integration, it can use both the Pi and Arduino in order to communicate with each other and in order to detect those markers accurately. This can be these images that are transferred from the Pi can be translated into intelligent decisions that are based on the state of the Arduino and the angles and positions that are given to the Arduino. The motor controller can accurately drive from one destination to another because of the collaboration between the Arduino and the Raspberry Pi, which allows us to receive and interpret accurate angles and positions, as well as different marker values, and allows it to successfully navigate a course.